Hello and welcome. In this video, I'll be covering another sorting algorithm, heap sort, which is again an n log n time complexity algorithm. But it is essential that we first understand the underlying data structure that it uses for implementing a sort. The data structure that I am talking about are called heaps. Let's begin by understanding what the heaps are. Interestingly, a heap is an array that can be visualized as a nearly complete binary tree. Let me take an example of some numbers, let's say 7, 8, 5, 3, 2, and 1. Let me also write down the index numbers over here: 0, 1, 2, 3, 4, and 5. Now, if we have to visualize this as a nearly complete binary tree representation of this array, let's start by drawing some nodes. Now, what I can do is from top to bottom and left to right, I'll be writing down the index numbers over here. 3, 4, 5, and 6. Now we can just plot each number to the corresponding index. I can just copy these numbers, whatever is there on the 0th index. 7, 1 is 8, at 2 is 5, 3 is 3, and 2 is at 4, 5 is at 1. So this is what we call a heap data structure. Now, how a heap is maintained within the array is with a mathematical equation which can be utilized to find what is the right child and right child of each node. If we see at this tree, we will be able to find that there is a pattern. Say I take I is 0 over here, and we can find the left child with the help of this equation 2i plus 1. And in the same way, we can find the right child index by using the equation 2i plus 2, and so on for each of the subsequent subtrees. We can quickly find what is the left child and right child if we just provide the value of I. Next, we would look at two important constraints that we impose on this data structure. These two constraints are where my root node is greatest or largest. So if I impose this constraint that root node will always be greater than of all these three values, let's say if I build a heap like this, and if I see that 3 is the greatest of all the three numbers over here, then this particular heap structure is satisfying the max heap property. Max heap property is maintained by the constraint that your root node should be the greatest of all the elements. It does not matter what is in the right child and left child, like are they greater than each other or anything. It does not matter. One can appear here or and two can appear there. That does not matter. Like even this particular heap is a valid max heap. Both of these heaps are satisfying the max heap property and they are called max heaps. Now what does max heap offer us? Max heaps offer us one particular thing, which is whenever you ask for the greatest number, it will always be the first number in the array. Okay, so if I write down the index numbers over here, 0, 1, and 2, 0, 1, and 2, then if I need to write these in form of array, my array will be like 3, 2, 1 for the first one, and for the second one 3, 1, 2. In both cases, I will be able to access the largest number at the first position, 0th index, in O1 time. So, max heaps offer us this particular feature where we can always get the greatest number in a fixed time or in a constant time, O1 time. That is the max heap. And if we just reverse the constraints, instead of greatest, if I make it minimum, then it becomes the min heap property, and in that case it is referred as min heaps. Before we move ahead to implement sorting using heap sort, let's look at some of the interesting facts about the heap data structure. Here I have two arrays of length 7 and length 4, and I have plotted them into their corresponding binary tree visualization. What we see from this is that anything that is indexed greater than or equal to n by 2, considering only the integer part of n by 2, where n is the length of this array, and we can safely ignore the decimal part because we don't have indexes in decimal, we only have integers as our indexes. So anything that is greater than equal to n by 2, in this case 3, are all leaf nodes. Okay, and anything that is less than 3 are actually representing non-leaf nodes. Okay, this is important because leaves in itself are heaps. They can be considered max heap or min heap. They are a valid heap because there are no child elements over here. This property will be useful for us to convert any array into a max heap or min heap. We will see that next, that how we work our way up from the non-leaf nodes till the root of this tree and then end up creating a max heap or min heap. In order to convert any array to a valid max heap or min heap, let's define a function called heapify that would just fix the heap property for one node at a time. What this heapify function assumes is that all the subtree below this root are a valid max heap or min heap, which means that if this is my entire binary tree, then there is only one node, root node is misplaced. That's what this function makes assumption. Now if we have to apply this function onto our arrays, then what should be our starting index, where the I should start from? If we go back to the previous diagram, we see that all the leaf nodes are already a valid max heap or min heap. That means we should start from one level above the leaf node, which is the indexes which are less than n by 2. Okay, in this case n by 2 is 3, in this case n by 2 is 2, so it has to start from less than 3, which is 2, index number 2. Okay, if we have to convert our first array into a valid max heap, we will start from index number 2, and then we will call heapify function, which will try to fix the position of root node represented at index I. Let's look at how this heapify function would be used to convert this array into a valid max heap. For this heapify function, what are the two important things? One, left subtree and right subtree are valid max heaps. This is one requirement for this function to work. Second, what is the terminal condition? Because we are going to call it recursively within the heapify function, then we must also know what the terminal condition is. So terminal condition is whenever the root is in its correct position, okay, if root is already in its correct position, then we can end calling heapify, or we can return from the function. Example, if we have a case like 9 1 2, okay, then we just return, because 9 is the largest of all these three numbers. We don't have to do anything. Third thing, if root is not at its correct position, if the tree is like 2 and then there is a root here which is root of my left subtree and it is 9, and then I have root of say 1 and this is my right subtree, then what is going to happen in this case? In this case, we will swap root with the root of my left subtree, okay, which is 9. So the largest number, had 9 been here, we would have replaced the root of right subtree with 2. And then 9 goes up. Now what happens in this case? We no longer can say, or like at least we are not sure if 9 was bubbled up and 2 was sent here, whether this would still be a valid max heap or not. We cannot say whether it's a valid max heap or not. So what do we do? Then what we do is we call the max heapify or heapify function with the index of this node. In this case, let's say if this is my 0 index, it is 1 and it is 2, then I will call heapify on 1 again. Okay. Although we are working our way up from bottom to top, like from this layer to the root node, but if a violation happens while trying to fix the root node, then I have to go back and call heapify on the node which was swapped with the root node. Okay. Let's see that in action. Let's start with the index 2 because this is where the non-leaf nodes start. Just looking at this right subtree, I can say that 7 is the largest of all these three numbers. So 3 comes down and 7 goes up. Now when we try to call heapify again on the index 6, because index 2 and index 6 were swapped. As soon as I try to call heapify with index 6, I see that this is a leaf node and we just return back from there. Okay. And now coming to the index number 1, which is our left subtree. We can say that 5 is the largest number, so 1 comes at the position where 5 was earlier, 2 remains at its own position. Now again we go to 0 and we see that 9 is already the largest number of 5, 7 and 9, so nothing happens and we stop calling heapify anymore. Now if we just write down these index numbers, and if I write down my array, it is 9, 5, 7, 2, 1, 6 and 3. Although earlier also my 0th index was giving me the largest number, but it was not a valid max heap. But in this case it's a valid max heap, because given any index, if you try to find out the left child and right child, the root node will be the largest of 3. Now the next step is how we can use this valid max heap to uh, finally sort the numbers in ascending order. The idea is fairly simple, that we pluck out one element at a time from this valid max heap, and by plucking out I mean uh, delete this element, and when we delete this element we send this element back to the last of this heap, and that portion of the heap will no longer be considered uh, in a max heap of this array. Okay, we'll see what does that mean. Let's begin by taking out 9 out of this valid max heap, and I can send it at the last position and swap it with the 3. The resultant array would be 3, 5, 7, 2, 1, 6 and 9. Now we don't want to consider this portion in our heap anymore. Either we can keep this element separately in a different array, maybe we can keep a copy over here in another stack, but then we will have the sorted elements here also in this copy. It's totally up to you whether you want to copy it somewhere else or not. This was our valid max heap. Okay, each root node is greater than its child elements. Now what we have done is we have removed 9 from here and we sent it at the position where 3 is. So 3 comes here and 9 goes here. We don't want to consider this in our heap anymore, and we want to call max heapify again on this node, root node, because this looks out of the position. This is not at its correct position. I will remove 9 in the last step. Okay, now if I call heapify on 0th index, what do we see? We see that 7 is the greater number of all the three numbers over here. Out of 3, 5, 7, 7 is the largest number. So we just swap 7 by 3. 7 comes here and 3 goes here. Now I have to again call max heapify on this node, because we might have disturbed the max heap property for this subtree. We check again, out of 6 and 3, 6 is the larger element, 3 comes here and 6 goes up. Now we don't have any more elements to go down. This was a leaf node, so it is a max heap in itself, and that is where we stop. Now my array is looking like 7, 5, 6, 2, 1 and 3. We don't want to consider 9 in the part of this heap, even though it is still present in the array. We do the same operation again. We swap 7 with the second last element in this array, and 3 comes at the position of 7 and 7 goes in the end. Now the array is 3, 5, 6, 2, 1 and 7. I also want to ignore these values because these are the deleted ones. We don't want to come and perform any operation over here in this portion of the array. Okay, now let's see how does the node look like. What operation we have done? We have swapped 7 with 3. So 7 has come here and 3 has gone up. Okay, now I don't want to consider this anymore in my heap. Now I call the max heapify again on the 0th index, and we do the comparisons in the same way like we did earlier. So out of 3, 5, 6, 6 is the bigger number. So 6 goes at the position where 3 is, and 3 comes here. And if we write down our array again, the array is like 6, 5, 3, 2, 1. Okay, and I had 7 and 9 already there. We repeat the same operation. We take out the first element and we swap it with the last element here. So 1 comes front, 1, 5, 3, 2, and my sorted portion is looking like 6, 7, 9 now. And I can plot this again. So what we have done is 6 was swapped by 1. So 1 came here and 6 came down. Now I don't want to consider 6 anymore. Now we call the max heapify again on the first or root node, which is out of the order here, which is 1, and we see that 5 is the greatest or the largest number here in comparison of 1, 5, 3. 5 goes at the position of 1 and 1 comes here. In this process, I might have disturbed the max heap property of my left subtree, so I call the max heapify again at the index 1, and then we just find that the left child was a greater number, so 1 goes to the position where left child was and 2 comes up. Now again the max heap property is satisfied. We end up with an array which is 5, 2, 3, 1. We still have 6, 7, 9 here, and this time we pluck 5 out and send it to the last, and we swap it with the 1. So we will have 1, 2, 3, and 5, 6, 7, 9. Even though it is looking like sorted, but from the max heap perspective, 1, 2, 3 is not a valid max heap. Okay, let's see what has happened. What we have done is we have swapped 5 with the 1. Now I don't want to consider 5 anymore in my heap, and I just want to have these um, remaining elements. Now what we have is again call heapify on the root node, and then in this case 3 comes up, 1 goes and becomes the right child. Now my array is 3, 2, 1, and we had our sorted portion 5, 6, 7, 9. Okay, now I do the same thing. I pluck out the maximum number, swap it with the last number in the heap, and 1 comes here, 3 goes there. We will have 1, 2, and then the sorted portion 3, 5, 6, 7, and 9. Now we can plot this again, and it is 1 and 2. In this case, we can see that okay, there are only 2 elements. They are both swapped, so it becomes 2, 1, 2, 1, and we had 3, 5, 7, 9. I again pluck out and swap it with the first element. My array is like 1, and then the sorted portion 2, 3, 5, 6, 7, 9. So this way I have like there's now only one element remaining which is sorted in itself. So the idea was like first build a max heap, then keep plucking numbers one by one from this max heap and keep swapping them with the last element in the unsorted or the max heap portion of my array. and do not touch anything which has been already plugged out from this max heap. Let's quickly implement heap sort in JavaScript. Let me begin by writing a function called heap sort, and let's accept an array as a variable. And within this function, let me write a function build max heap, build max. And as we saw, like during build max heap, we have to work our way up from non-leaf nodes, which start from 1 less than n by 2, where I can say I equals to floor and where n is my length of array, and I can subtract by 1, and then I have to go till the root node, which is 0. And then what we have to do is we have to heapify. Heapify means we have to fix the max heap property for one single node at a time. Okay, and let me write the heapify function here. That's ith node, and what I have to do is I have to find the left child and right child. Left child could be found with the condition or equation 2i plus 1, and let right child be 2i plus 2. Now I have to also ensure that I am well within the bounds of this array. For that, what I can do is I can pass the max index element, like what is my last index number. So what I'm going to do is from here I'm going to pass the last index number of my array. Also, let's take a temporary variable called max I, and let's assume that it is the root itself. Let's compare and see if my left child is in the bounds of this array, and I accept this in as the end parameter. If it is, then I want to compare whatever is my left child, is that greater than my max I element or not. Currently max I is root, and if this condition is true, then we assign max I as left child. Okay, and I do a similar comparison for the right child, where I have to check whether it is still in the bounds of array. We will see the significance of this check of keeping right child and left child indexes within a bound of last element or within a specific range, what is how it will be used. Okay, and ARR right child is greater than ARR max I, then again max I is set to right child. Now what do? We just swap max I with the root. Okay, and if my max I is not equal to I, which is like in this process of swapping max I with the I, we would have either disturbed the maxi property of left subtree or right subtree. So what we have to do is we have to go and fix the heap property at max I. Okay, and we have to go till the last element, and once this is done, uh, it would have resulted in a max heap. Okay, now what I'm going to do is from here I'm going to call the internal function build max heap, and I'm going to just return an array. Let me also write the swap function. So this is a simple swap function, and we can run this program to verify whether it is currently returning as a valid max heap or not. Right now the sort is not implemented. It's just converting the array to a valid max heap. Let's see if that works or not. I have taken the same numbers that we took during our dry run. Okay, 9572163. So this returns a valid heap. Let's now implement the sorting as well. For sorting, what we have to do is we have to utilize the max heap property, which is like every time access the zeroth element in this array, that would be the maximum element. So I will run through, like I will pluck the elements, all the n elements from this heap. Okay, so I will go till the length of array, and as soon as I take out the zeroth element and send it back to the end of array, which is arr dot length minus 1. So I have to send it at the last of the array, in the end of this array. Now every time I have to move by one position, so I am also reducing it by I, because once I have deleted this element, or once I have moved out or plugged this element out of the heap, I don't want to go and touch this element back again. Once the element has been taken out from this heap, what I would have done is I would have disturbed the max heap property at 0th index. So I have to go and fix this heap property at 0th index. I can do that by calling heapify function, and at this time I don't have to go till the entire length of the array. What I have to go is, like, I have to ensure that I do not go and operate on the numbers which have been recently deleted. So I am going to use one less index. Instead of -1, it is -2 and -1. So it has to stop before the position where the maximum element was placed. If maximum element was placed at, let's say, 9, index number 9, then my heapify, or my heap, is valid till only 8th index. I don't want to consider the 9th index. So this is it, and let's see if this is giving us a valid sorted array or not. 1 2 3 5 6 7 9. Yeah, so the numbers are now sorted. This is the implementation of heap sort in JavaScript. Thanks for watching. This has been a long video.